Hi, I'm Kalu, and I'm going to be doing the ball swinging on a rope problem. So here we go. It's set up here. Um, but so it starts a ball on a 1 meter rope with that's at an angle of theta 1, which is 31.6 degrees. The mass is 0.72 kilograms, and it swings and then it releases at an angle of theta 2, which is of 14.8, and we're trying to find the distance between this point right here at from the bottom of the directly down from the hook that the string is attached to. We're trying to find the distance between that point and where the ball lands. So what we need to know for this is energy. We have our conservation of energy, meaning that the energy at any point during this is going to be the same at any other point. So we have a couple of forms of energy. So this is true in the entire universe. At any point in the universe, it's going to be the same amount of energy than at any other point in time in the universe. So this is going to be an isolated system that we have. So it's going to go from having just gravitational potential energy, which we model as m times g times h. So that's this is specifically gravitational potential energy, but I'm just going to say EP for potential energy. And then we have our kinetic energy, which is modeled as half mv squared. So here this was for gravitational potential energy. The m was mass, g was the gravity of Earth, and h is the height. And then for this one, it's mass and velocity. So that's for the kinetic energy. So at any point in time, take any point in time, you add up the gravitational potential energy and the kinetic energy, and it should be the same no matter what point in time you're at. So we have that. That's going to be a big chunk of it. We're also going to talk about kinetics. So kinetics is the main equation we're going to use is this one, which is delta x is equal to v naught t plus half a t squared. So t is for time in seconds. Delta x is the change in position in meters. V naught, v is velocity, but v naught specifically means its initial velocity. So that's its initial velocity, and then a is the acceleration. So if acceleration is changing or like different at any point, then we can't use this, but in this scenario, the acceleration is going to be gravity, which is always going to be the same 9.81 meters per second squared. So that's going to be the same, and we can use this equation. Also, we need to learn a little bit about trigonometry. So for trigonometry, it's figuring out certain ratios of side lengths of triangles. Sorry, that's a little close, so let me move it here. Should be good. So we have a couple. Let's call this angle A, and this angle B. And our third angle is a right angle. We can only do the things I'm about to talk about if we have a right triangle. So we have sine, cosine, and tangent. We're really only going to worry about sine and cosine, but in order to figure out what they are, there's a mnemonic device to remember, which is SO, CA, TOA. So, O means opposite, A A means adjacent. Adjacent. And H means hypotenuse. So S is for sine, C is for cosine, and T is for tangent. So we know that this is the hypotenuse of this right triangle. And the adjacent and opposite sides are going to be different depending on what angle we're talking about. If we say for angle A, our adjacent side is going to be this one. Their opposite side is going to be this one. The reason that's the adjacent side is because the other side that is adjacent to it is the hypotenuse, but that has its own thing. So, so that's our adjacent side. For angle B, this one would be the opposite, and this one would be the adjacent. So, these SOHCAHTOA things mean a ratio. So let's take sine of angle A. So sine A. Sine A is equal to the opposite over the hypotenuse. So see how this is a ratio of the length of the opposite side and the length of the hypotenuse. Now that we have this set up, let's say we know the length of the hypotenuse and we know what sine A is. Then we can figure out what the opposite side length is by multiplying both sides by h. Let me clear those underlines. There we go. So multiply both sides by h. These are going to cancel out, be 1. So that means that h sine A is equal to the length of your opposite side. There you go. Cool. And then, so with all of that, we're going to bring back the kinematics that we talked about a little bit ago. So, if we have some little particle that has a certain initial velocity, it's going to follow this trajectory. And so, let's split this up into its component velocities. It's going to have a certain velocity in the x direction and a certain velocity in the y direction. So, if we remember our trigonometry we just did, we know this angle here. Let's call this theta. There we go. So we have our initial velocity, which is the hypotenuse of this triangle. And then let's take cosine of theta is equal to the adjacent over the hypotenuse, so SOHCAHTOA over here. So the adjacent side is this one here, and let's call that the velocity in the x direction. So I'm going to call that Vx. And then the hypotenuse is your initial velocity. So if we multiply both sides by v naught, then we get v naught cosine theta is equal to Vx. Cool. Alright, let me erase it and copy it down over there. So, this is V naught cosine theta. And we can see that the Vy over here, so this Vy, is going to be the exact same thing as this. We just moved it so that it's right on the particle. So it's going to be the same as trying to find that side. So sine V naught, sine theta, oopsie, sine of theta is equal to Vy over V naught, because the opposite opposite side here is the same as this here. That arrow over there, that's Vy. So then we can see that Vy is V naught sine theta. Cool. So that's what we have to know for projectile motion. And then the last thing is that, actually one more thing for projectile motion, is that there's no acceleration in the x direction because we're saying that there's no air resistance. So at any point in time, let's say this one, and this one, the velocity in the x direction should be the same thing. I'm going to make it a little smaller so they all fit here, but let's pretend they were all the same thing. So, all the same thing. But for in the y direction, there is an acceleration on it, which is gravity. So here, it's still going up, but a little less. And then here, it's actually not at the top of the parabola. That's the shape it makes as it flies. So here, it actually has no velocity in the y direction. And then as you keep going down, acceleration is acting on it downward more, so the velocity is changing and it's moving down. So down over here, it has a negative velocity in the y direction. There we go. That's what we have to know. Okay, so to solve this, let's set up our energy equation. So initially, I'm going to erase my. So initially we have mg h1, that's our initial height, plus half m v naught squared, that's our initial velocity. That's going to be equal to, so this is the moment in time, this one over here, and now we're going to talk about this one. So then it's going to have mg h2 plus half mv squared. I'm just going to say v because it's a different velocity, it's not the initial one. So in order to find the height, let's take the initial one. So we have, this is where the rope would be at rest, this is the thing, and then this is our 1 meter. So this is theta 1. And we know that this is going to be this side length here is going to be, of this triangle, is going to be 1 times cosine of theta 1. So, sorry, that theta looked like a 0, I'm fixing it up. So, 1 times cosine theta 1 is cosine theta 1. So this is cosine theta 1. And so, we're going to set our reference height to be at 0.25 meters off the ground, so at 1 meter from the roof. So that means this height here, this here is our height in between those lines, is going to be 1, because this whole thing here is 1. And the other section is cosine theta 1. So this height is 1 minus cosine theta 1. So it's mg 1 minus cosine theta 1. And then its initial velocity is 0. Or, sorry. So if the velocity was 0, 0 squared is still 0, and then this whole term is going to be 0. So that's all for this side. The other side, it's going to be the same thing for the height, just with theta 2. So that's mg 1 minus cosine theta 2. And it's going to have some velocity that we're going to try to figure out, plus half mv squared. So I'm going to move this term to the others. Oh, first I'm going to divide everything by m, so all of these are going to cancel out and become 1. And then I'm going to move this to the other side and factor out g, which is going to simplify stuff out. So that's going to be equal to g times cosine theta 2 minus cosine theta 1. So once that's moved to the other side and g is factored out, those 1's cancel out, and the negative cosine theta 2 is a positive theta 2. That's equal to half v squared. Then multiply everything by 2 and square root both sides, and we get 2g G did not work out. 2G cosine theta 2 minus cosine theta 1 square root of all of that is equal to V. So over here, I have that whole thing. This here, I substituted in theta 1, theta 2, and G for the values, and we get this as our velocity, 1.5027, lots of stuff. So, I'm just going to keep it as V because it's easier to work with. Let me erase some stuff. I'll be right back. Okay, so now we have basically a projectile motion problem because we know what the initial velocity is. Let's just figure out the angle. So it's cut at an angle of theta 2. Oof. I have a lot of problems with this tablet. Theta 2. There you go. Ball is cut there. So we can see that this is theta 2, and it's going to be moving in an arc which traces out the part of a circle, and its velocity is going to be perpendicular to the line between the center of that circle and the mass itself. So this is its velocity. Since this is theta 2, this is a 90-degree angle, and this is horizontal, and that was horizontal, this one's vertical. That means this is also going to be theta 2. So, let's use our other kinematics equation, which is, it was delta x, but let me say delta h, change in our height. Actually, no, I'll just say delta x is equal to v naught t plus half a t squared. So, our v naught is specifically our vy, our in the y direction. So, and our a is going to be g. So let's figure out the change in height. That's going to be the final minus the initial. So the final height is 0 as it hits the ground. That's what we're trying to find. And then the other height, is the same thing as we were doing to find the height from the 0.25 meter, it's going to be this height here, and so we know this height is cosine of theta 2, and the whole thing is 1.25. So this is 1.25. Sorry, this is supposed to be minus, not multiplied. 1.25. Yeah, let me erase that because it's 0. It's just going to be whatever the other one is. So it is negative. Has the 0 here. So 0 minus 1.25 minus cosine theta 2. So that 0 shouldn't matter. And then our Vy is going to be sine theta. Sorry, that theta is squared. That's supposed to be theta 2. So sine theta 2 times V naught. Put that V naught up in front. And then it's going to be plus half at squared, but we know that gravity is downward, so that's the negative y direction, so it's going to be minus g over 2 t squared. Oh, I forgot the t here. Don't forget that one. So if we rearrange some stuff, we're going to get a quadratic, and so I have this quadratic here, this one, which has our velocity, sine theta, all of that, and we find 2 values for our time. We aren't working with negative time, so we're only dealing with this one. We find that our time is 0.2857. So we know that our distance traveled is our x velocity, so our vx times time. But in order to find the full distance, we know that it's going to be from this point down here, remember, not from where it's released. So we have to add this distance. And so the other one was the vertical distance was cosine theta 2, so this one is going to be sine theta 2. So plus sine theta 2. So this is our distance. So we have our Vx is our V naught times cosine theta 2, sorry, it's sloppy, times our time plus sine theta 2. And so that's going to give us our final answer in meters. And then, oh yeah, our time thing we got a little bit ago was in seconds. So we have here, we have to figure out how many significant figures we can use in our answer. And so we never actually used mass. We used mass, but it got canceled out somewhere along the way, so we can ignore it. This one has 1, 2, 3 significant figures, and this one has 1, 2, 3 significant figures. So since both of them have 3 significant figures, we can only have as many significant figures as the measurement that we have that has the least. And since they both have 3, that means the least is 3. We're going to have 3 in our answer. So this is our final thing. This is our time. This is our initial velocity, cosine theta 2, and then sine theta 2. That's what we figured out. So for 3 significant figures, it's going to be 0.666 meters. There we go, because we've rounded to that third decimal point. All right, cool. There's our answer.